Welcome to YouTube channel Tech Guru Gautam Prasad. In this video, we are going to discuss DC motor fundamentals. DC machine can be classified into two categories. A DC machine could be a generator or it could be a motor. The DC generators are used to convert mechanical energy into electrical energy, whereas a DC generator converts electrical energy into mechanical energy. In order to understand the operating principle of the DC motor, it is necessary to understand how does a current carrying conductor experiences force when it is kept in the magnetic field. So here there is a straight conductor that has been placed in the magnetic field being produced by two magnets north and south. The current carrying conductor through a conductor is in anti-clockwise direction. Due to the presence of the two magnetic fields simultaneously, an interaction between them takes place as shown in the figure. So one magnetic field is due to the current carrying conductor and the other magnetic field is being caused by the permanent magnets. These two magnetic fields interact and the conductor experiences a force. Here the DC motor has been shown. So DC motor has got a rotor coil. Uh, it has got magnets, permanent magnets or electromagnets on the stator. It also has commutator on the rotor fixed on the rotor shaft that is connected with these coils on the rotor, and it has got a shaft on which the rotor rests. In short, all these parts are there in the DC motor. Now let's discuss the force on the current carrying conductor. So there is a conductor placed in the magnetic field between two permanent magnets, north and south pole. So as soon as the current starts flowing through the conductor, it produces its own magnetic field, and its magnetic field has been shown by equidistant circles, concentric circles uh, with the conductor at the center, and you can see the magnetic field caused due to the current carrying conductor is interacting with the magnetic field caused due to the permanent magnets, and the result is that the straight lines of force, magnetic lines of force caused by permanent magnets is getting distorted as a result. Here also this arrangement has been shown where a small commutator has been connected with the conductor and the conductor is being rotated in the magnetic field. So being rotated in the magnetic field because of its own force that it is experiencing. So when this single coil has been shown for the simplicity of understanding, and this single coil has been connected with the help of a battery. You can see the positive terminal and the negative terminal has been connected. As such, the current is passing through the coil, and uh, as in the earlier slide, it was shown that current flowing in the conductor is causing its own magnetic field, and it is interacting with the field being caused by the permanent magnets. So as a result, the conductor is experiencing force and it starts rotating. The direction of the force has been shown with this red arrow, as I'm trying to show you from with the help of my pointer. So here it is. You can see these two forces are acting in opposite direction and trying to create a couple of forces that are acting opposite to each other, and a couple of forces try to rotate the conductor. As a result, this conductor starts rotating. Now think of a situation if you know number of coils is being uh, increased in terms of it is put on the periphery of the rotor, not a single coil, but multiple coils are kept on the periphery of the rotor. So, uh, in turn, what will happen? Uh, the force will be caused that will cause the rotor to rotate, and gradually uh, different conductors will be facing the lines of force one after another, and they will keep on experiencing the force, and thus the rotor will keep on rotating in a certain direction because of the constant uh, force that is working on the conductors. So here it is being made clear further that the amount of force that the conductor is experiencing is a multiplication of its length, the amount of current, and the magnetic field density. B is the flux density uh, in which the conductor is kept. The B is the flux density of the field being caused due to the permanent magnets here. So here also the same thing has been repeated, and the number and the commutator has been shown. The direction of the current has also been shown, and this is it. Here uh, it has been shown that as the angle is increasing or decreasing at an angle of 90 degree, the force is maximum because the force is not just equal to IBL sine theta, IBL, but also sine theta is multiplied with that, so that it depends on the angle at which the conductor is facing the permanent magnetic field. So, if it is at an angle of 90 degree, then the force is maximum because sine 90 degree equal to 1. But suppose if it is at 30 degree, then sine 30 is half. So only half of the force will be exerted on the conductors. So as it is going to 0 degree, then zero force it will experience. So the magnetic neutral axis can be imagined to have where the conductor will experience no force. So force carrying conductor, as shown in the figure, the flux lines produced by the magnet and the conductors are in opposite direction to each other at left side, and hence cancel each other, and therefore no flux lines at the left side of the will be reduced. At the right angle, the individual fields are in the same direction, and hence will add and strengthen each other, and therefore number of flux of lines right side will increase. So the same thing that I have already explained, that BIL sine theta is the uh, formula with the help of which we calculate the force on the conductor, and the force on the conductor, current carrying conductor, and the direction of the force. The direction of rotation of the motor depends on the direction of the force exerted on the armature winding, and the direction of the force experienced by the current carrying conductor is given by the Fleming's left hand rule. And what does the Fleming's left hand rule states? It states that if first three fingers, let me show you uh, better here. In this slide, you have been shown that your forefinger, middle finger, and thumb have been stretched as such they are perpendicular to each other. Now, if you know your forefinger is in the direction of the magnetic field, and your middle finger is in the direction of current in the conductor, then your thumb will, represent the direction of the force on the conductor. So with the help of Fleming's left helm rule, you can predict the direction of force exerted on the conductor in the case of DC motor. Now, winding in the DC motor. There are two types of the winding the DC motor employs. Uh, these are field winding and armature winding. Out of these, the field winding is a stationary, which is on the stator, which does not move at all, and the armature winding is mounted on the shaft or the rotor, so it can rotate freely. Connections of the winding for the for operation of the motor to operate the DC machine as a motor, the field winding and the armature winding is connected across the DC supply, as it was shown in the picture that it was connected with the help of a battery, but in actuality it is connected across the DC supply. Principle of operation of the DC motor. When current carrying conductor is placed in the magnetic field, it experiences force. That is the basis of or the principle of operation of the DC motor. In the case of the DC motor, the magnetic field uh, is developed by the field current, and the current flowing in the field winding and the armature winding play the role of the current carrying conductor. So the armature winding experiences a force and starts rotating in as a result. Now here the construction of the DC motor has been shown in the picture. You can see number of poles are projecting from the stator, and there is a rotor placed in the center, and the brushes are also there resting on the commutator. So you have poles, and the pole winding is also you have the winding. You have to feed DC power to the poles also, so that they create electromagnets uh, under the influence of which your rotor conductors are placed, and they experience force and they start rotating. So important parts of the DC motor are yoke, field winding, armature, commutator, brushes, and gear. Gear means brush holders with gearing mechanism. Yoke is this one. You have the terminal box. You have lift eye, with the help of which you lift the motor frame and foot of the yoke. Now you have poles. Poles of the DC motor is an electromagnet. The field winding is wound over the poles, and poles produce magnetic field when field winding is excited. Field winding, the coils, you can see in the picture that coils are there, wound around the pole, and the coil wound around the pole are called field coils, and they are connected in series with each other uh, to form field winding. When current passing through the field winding, magnetic flux is produced in the air gap between the pole and the armature. Now, armature. Look at the armature as shown in the picture. Armature is the cylindrical drum mounted on the shaft, in which the number of slots are provided, and armature conductors are placed in these slots, and these armature conductors are interconnected to form armature winding. Commutator is a cylindrical drum mounted on the shaft along with the armature core. It collects the current from the armature conductors and pass it to the external load via brushes in the case of DC generators. But in the case of DC motor, these commutator bars collect current from the DC source and feeds it to the uh, armature coils so that it creates its own magnetic field and interacts with the permanent electromagnets magnetic field created due to the poles. Now here you have seen you can see the brushes on the screen, and the brushes are placed in the brush holder, and they are you know pushed through the spring pressure so that they rest with the pressure on the surface of the commutator, and the current conduction takes place smoothly. Commutator is a rotating part of the DC motor, so it is not possible to connect the load directly on it, and hence the current is conducted from the armature to the external load, or in the case of the motor, it is just opposite by the carbon brushes, which are held against the surface of the commutator with the help of springs. Here, different parts of the DC motor has been shown. Now, there is something very significant that is called back EMF, and this back EMF needs to be discussed in detail because this is something which is very important to understand in the case of the DC motor. When the armature winding of the DC motor starts rotating in the magnetic flux produced by the field winding, it cuts the lines of magnetic flux. And as you know, according to the Faraday's law of electromagnetic induction, if the conductors are cutting the magnetic lines of force, an EMF will be induced in the uh, conductors. Or here, the armature winding, in the armature winding, EMF is induced. And as per the Lenz's law, this induced EMF will oppose the very cause that is producing it. So the motion because of which it is being produced, it will start opposing that motion. So there will be a magnetic drag in the conductors. Yet the conductors will have to overcome that force. So the presence of the back EMF makes the DC motor self-regulating machine, and it makes the motor to draw as much armature current as it is just sufficient to develop the torque required by the load. When the motor is running on the load, a small torque is required to overcome the friction windage losses, and therefore the armature current IA is small and the back EMF is nearly equal to the applied voltage. Nearly, mind it, it is nearly equal to the applied voltage. If the motor is suddenly loaded, now think of a situation. If the motor is suddenly loaded, the first effect is to cause the armature to slow down. Now, the speed of the motor will slow down because of heavy loading, and therefore, the speed at which the armature current moves through the field winding is reduced, and hence the back EMF falls. In this case, because the speed has reduced, the cutting of the flux by the conductors will also reduce, and that will reduce the back EMF in the conductors. So this decreased back EMF allows a larger current to flow through the armature. Now, EV is uh, lowered, so the current is increased to increase the torque delivery that will help the motor to achieve further higher speed, and thus the driving torque increases and the motor slows down the motor will stop slowing down when armature is just sufficient to produce the increased torque required by the load. Now, if the load on the motor is decreased, now suddenly if the load is decreasing, what will happen? The speed of the motor, the speed of the motor will increase. It will tend to increase because it is getting relieved in terms of load. So what will happen? More number of flux will be cut by the conductor and EMF, back EMF will be more. So if the back EMF is more, now IA current, armature current will decrease. So this I am explaining you to show that how this DC motor becomes self-regulating with the help of this back EMF. So back EMF is something that makes DC motor self-regulating in nature. And this is very important to understand, my friends, for the electrical engineers. The motor will stop accelerating when the armature current is just sufficient to produce the reduced torque required by the load. It follows, therefore, the back EMF of the DC motor makes DC motor self-regulating. So, back EMF has been explained in a better manner in this slide. This is the armature and this is the voltage supply with which it has been connected, causing an armature current of IA. Now, because of the rotation of the armature, there is an induced EMF in the armature conductors, and that is called EB. Now, EB stands against the voltage V applied. RA is the armature conductor, resistance of the armature conductor, and EB is the back EMF induced in the armature conductors. So this voltage is just in stands against this B, the applied voltage, and the voltage supply is connected here. So the whole connection of the armature looks something like this. So there is a battery. B is the B has been replaced with the battery, which is the supply voltage, and there is a resistance of the armature conductor RA, and EB is you know against the um, applied voltage EB. So here is the complete picture of the uh, equivalent circuit. You can consider it with the help of armature voltage and back EMF. So back EMF, the armature conductor supply voltage V has to overcome the opposition posed by the back EMF and some other voltage drops such as brush drop and the voltage drop across the armature resistance. So the complete equation of the voltage applied becomes V is equal to EB, that is back EMF, plus the drop in the resistance, armature resistance, plus brush drop. But the voltage drop across the brushes is negligible as compared to EB, and IARS. So that can be neglected. So the consequent voltage can be shown with the help of equation number 2, that is V equal to EB plus IARA. Now there are different types of the motors, DC motors, depending on the ways of connecting of the armature and the field winding of the DC motors. DC motor can be classified into following different types. So the DC series motor, the DC shunt motor, the DC compound motor, and DC compound motor is further divided into two types: short shunt compound motor and long shunt compound motor. There is yet another type of the DC motor that is called separately excited DC motor, in which the field winding is connected to a separate source of DC voltage, and that is not connected to the armature winding of the DC motors. In the Other types of the DC motors, like DC series motor, shunt motor, and compound motor, the field winding is connected with the armature winding, so they are different from this separately excited motor. DC shunt motor. In this type of the motor, field winding is connected in parallel with the armature. So this is called DC shunt motor. Or you can say the field winding is connected in shunt with the DC armature, DC motor's armature. The resistance of the shunt motor is always much higher as compared to the armature resistance. And this is because the number of turns of the field winding is more than the armature winding. In DC motor, the field windings are connected in parallel as shown in the next figure. The figure is after few slides. The field winding current ISH always remains constant because the resistance is constant, the resistance of the field winding is constant. And since V and RS both are constant, hence the flux produced by this field winding is constant. Because field current is responsible for the generation of the flux, phi SH is directly proportional to ISH. And this is why the shunt motor is called the constant flux motor. Here is the picture that you were looking for. So field winding is on the left side, as you can see here, and this field winding is connected in parallel with the connections of the armature. Armature is connected to the voltage source V, and here is the load current, complete load current, and this load current is divided into two parts, the armature current and the shunt field current. So, and these two currents are now going back to the source. So the circuit is being completed like this. In the case of the DC series motor, the field winding is connected in series with the uh, uh, armature winding. Thereby, that is why it is called series motor. And the resistance of the series winding is much smaller as compared to that of the armature winding, and the flux produced is proportional to the field current. And but this in this series motor, field current is the same as the armature current, so we can say phi, because of this series winding, is directly proportional to IA, that is armature current. So, and armature current is uh, the same as load current or the source current. So phi can also be termed as proportional to IS. So here is the picture, my friend. This is the armature current, or IS is the same, and this is the series field winding, which has got a resistance of RSE, which is much less than the armature resistance, and the whole connection looks like this. This armature current, and hence IA, and hence the current IS will depend on the load, and hence the DC series motor flux does not remain constant. With the varying load, this current will keep on changing, so the field strength will also keep on changing. Now, let us look at the compound DC compound motor. Long shunt compound motor and short shunt compound motor. There are two types of the motors that we will see in the next slide. Here is the slide. This is a series winding which is connected in series with the armature, and this is the shunt winding. So this type of motor basically have both the types of the winding, series winding as well as shunt winding. That is why it is called compound motor. And uh, the characteristic of such motors is the combination of both series and shunt type of the motor. Here, this is a motor that is called short shunt compound. In the earlier motor was long shunt compound. Uh, the series field is not connected uh, across the shunt field and the armature, or you can see shunt field is not connected across uh, armature and series field. The series field has been connected separately, and that is not being covered by the shunt field. Therefore, it is called short shunt compound. Both are compound motors, but here the configuration of the connection is different. So that is why it is called short shunt compound. The behavior is a little different from the earlier one. Torque equation: the torque produced by the motor will always be proportional to the air gap flux, and this air gap flux is uh, uh, proportional to the flux being caused because of the you know flux being caused because of the shunt winding or series winding or the compound winding, and the flux being caused by the armature. That means T is directly proportional to phi Ia. Phi is the flux uh, because of the shunt field or the series field, and Ia is the uh, armature current. And the flux produced by the field current is phi, and that is proportional to the field current. That means phi is directly proportional to I field. So torque is becomes thus proportional to the product of armature current and the field current. So here in the case of the shunt motor, this phi is basically constant. So we can say torque is directly proportional to armature current, and hence the torque is proportional to the armature current only. And the torque field equation of the DC series motor, if you will look at, then T is directly proportional to phi Ia, but phi is again directly proportional to Ia because in the case of the series motor, the field is connected in series with the armature. That is why phi is directly proportional to Ia. So T becomes directly proportional to Ia multiplied by Ia once again. So T ultimately becomes directly proportional to Ia square. And here it concludes that the torque of the DC motor is directly proportional to the square of the armature current, which is very significant discussion. And that is why the torque armature current the graph or the plot is not linear, as it was linear in the case of shunt motor because it was just directly torque was just proportional to the armature current only. Now the speed equation of the DC motor, we know that EB is directly proportional to N and P and phi and Z and the number of parallel paths. So EB is equal to phi Z and P by 60. This is the formula. And with the help of this equation, we can calculate the speed of the motor, that is N. So that N, if we look at EV is directly proportional to phi N, and N becomes thus proportional to EV by phi. Now, K is a proportionality constant here in this equation, and N is equal to K into EV by phi. Now, EB happens to be equal to V minus IARA as derived from this equation. Now, N becomes directly proportional to this V minus IARA upon phi. So, phi is directly proportional to I field current. We can write N is directly proportional to V upon IARA, V minus IARA upon I field. So, this is the ultimate equation here. In the case of the DC motor, N is directly proportional to V minus IARA because flux is constant in this case. So We are not considering that. DC series motor, in the case of DC series motor, this N becomes proportional to V minus IARA minus ISRS divided by IA, where EV is equal to V minus IARA minus ISRS, because series field is connect in series with the armature. So both the resistances drop uh, drops because of both the resistances, series field resistance and armature resistance has been subtracted from the voltage. Torque speed characteristic of the DC shunt motor. So torque speed characteristic, if you look at for the DC shunt motor, it is almost linear. Gradually, decreases with the speed decreases with the load. If you the torque demand from the motor is increasing, the drop uh, uh, very less speed drop is observed, and this is called a drooping characteristic. Not exactly linear, but with the increase of the torque demand, a slight drop in the speed, happens. In the case of the DC series motor, as because this torque was directly proportional to Ia square and N is directly proportional to 1 upon Ia. So this case torque armature current torque speed characteristic is different. Here, with the increase in the load, as because the field is becoming stronger. So the speed decreases very fast with the increase in the torque demand. So as you demand more torque or you load the motor heavily, the drop in the speed of the motor is very significant. In the case of the DC compound motor, which carries a characteristic which is uh, uh, very combination of these two. So here we have got two types of the compound motors. One is called differential compound motor, and the other is called cumulative compound motor. This cumulative compound motor can be used in some of the applications, but a differential compound motor has got such a characteristic that it cannot be used for any practical purposes, because its speed goes dangerously high, and it will not work for any practical case application. The torque speed characteristic, series motor application has, finds its applications in the electric train, diesel locomotives, cranes, hoists, trolley cars, trolley buses, rapid transistor system, conveyors, etc. A cumulative compound motor has got application in elevators, rolling mills, planers, punches, shear applications. Torque speed characteristic of the differential compound motor is not conducive to the loads. That is why it is not used. Specifications of the DC motor. Some of the important specifications of the DC motor are as follows: output power in horsepower or kilowatt, rated voltage, the type of the field winding, excitation voltage, base speed of in RPM, current, frame size, and rating and duty also. So here is a typical rating of the DC motor that has been shown. Output 3 HP motor, 230 volt series wound, and 230 volt is the excitation voltage. Insulation class is B, 1000 RPM is the base speed, current is 11 amperes, frame size 1 is 132S, rating is continuous, and SR number serial number is 840858. Series parallel control of the DC motor. Here is the series parallel control. Two series motors have been connected in series, and in the other case, two series motors have been connected in parallel. In either case, the speed of the motor will be different. So here is a possibility of series parallel connection uh, speed control. There is a rheostat connected in series with the series connected two series motors, and here there is a provision of in the same configuration connecting them in parallel and having the rheostat connected in series with the two motors. Thank you very much for being patientful and listening the whole discussion. Thank you so much. Please stay tuned with the YouTube channel Tech Guru Gautam Prasad. Like, comment, and subscribe. Thank you so much.